Hi everyone, welcome back to my channel. In this video, I am going to solve surface chemistry CSIR NET previous year questions from 2025, and also I have solved 2011 to 2024 previous year questions. That link I have mentioned in description. Please go through that. Now let's move to the question. Question 1 asked in CSIR in June 2025. In a colloidal solution, the zeta potential is the electric potential at the four options given. A, radius of the colloidal particle, B is radius of Stern layer, and C is radius of shear surface, and D outer radius of diffusion ion layer. We'll see the solution. The zeta potential is the electric potential at the slipping plane of a colloidal particle. Here Stern layer, that is a layer of firmly attached counter ions surrounding the colloidal particles. Next is shear or slipping surface, that is the imaginary boundary where the liquid moves relative to the particle during electrophoresis. The electric potential at this surface is called the zeta potential. Now, the diffuse ion layer extends beyond the Stern layer, but the zeta potential is not measured at its outer edge. Therefore, option A, radius of the colloidal particle, also wrong, and option B, radius of Stern layer, also wrong. Option C, radius of shear surface is the correct answer, and option D, outer radius of diffusion ion layer, that is also wrong. So correct answer is option C, radius of shear surface. Now we'll see the second question. This has asked in CSIR in December 2025. The expression for fraction surface coverage theta A for the dissociative adsorption A2 gas gives rise to 2A surface in the presence of an inhibitor I of G gives rise to I of surface. Competing for the same site is here given. Ka and Ki are equilibrium constants for adsorption of A2 gas and I gas respectively. Pi is the partial pressure of the ith gas. Here four options are given. Option A, Ka half into Pa to the power half divided by 1 plus Ka half Pa to the power half into 1 plus Ki Pi. Option B is Ka to the power half Pa to half Ki Pi divided by 1 plus Ka half Pa to half into 1 plus Ki Pi. And option C is Ka half Pa to half Ki Pi divided by 1 plus Ka half Pa to half plus Ki Pi. And option D is Ka half Pa to half Ki Pi divided by 1 plus Ka half Pa to half plus Ki Pi. Now let's see the solution. For the dissociative adsorption, A2 of gas plus 2S gives rise to 2A of S, and the inhibitor adsorption I of gas plus S gives rise to I of S, where S denotes a vacant surface site. Let theta A is equal to fraction of surface covered by A, and theta I is equal to fraction covered by inhibitor, and theta S is equal to fraction of vacant sites. Step 1, Equilibrium expressions. For dissociative adsorption, Ka is equal to theta A square divided by Pa2 theta square into S. Therefore, theta A is equal to root of Ka into Pa2 into theta S. For inhibitor adsorption, Ki is equal to theta I divided by Pi theta S. Hence, theta I is equal to Ki Pi into theta S. Now, we'll see the step 2, site balance. Since both species compete for the same adsorption sites, theta s plus theta a plus theta I is equal to 1. Substituting the above expression, theta s plus root of ka into pa2 into theta s plus ki pi theta s is equal to 1, or theta s is equal to 1 divided by 1 plus root of ka pa2 plus ki pi. In step 3, we'll see the surface coverage of A. Substituting theta S, theta A is equal to root of KAPA2 divided by 1 plus root of KAPA2 plus KIPA. Matching with the option, this expression corresponds to option D. So option D is the correct answer here. And now we will move to the third question. This is asked in CSIR in December 2025. A graph of surface tension of an aqueous solution of a surfactant as a function of concentration gives a slope d gamma divided by d ln into c by c naught of minus 4.8 into 10 to the power minus 3 nano per meter at 298 Kelvin. The area in Armstrong square occupied by each surfactant molecule at the surface is closest to, that is given C0 is equal to 1 mole per liter, and options are given as 41, 62, 83 and 104. Now we'll see the solution. Here use the Gibbs adsorption isotherm. Here given slope d gamma divided by d ln c, that is equal to minus 4.8 into 10 to the power minus 3 Newton per meter, and temperature T is equal to 289 Kelvin, and C is equal to C0 is equal to 1 mole per liter. Now we'll see the step 1, Gibbs adsorption equation. For a non-ionic surfactant, eta is equal to minus 1 by RT into d gamma divided by d ln c. Substitute the values. Eta is equal to 4.8 into 10 to the power minus 3 divided by 8.314 into 289. That is equal to 4.8 into 10 to the power minus 3 divided by 2402 divided by 7, that is equal to 1.998 into 10 to the power minus 6 mole per meter square. Now we'll see the step 2, area per molecule. The area covered by one molecule is A is equal to 1 divided by Na of tau, where Na of eta, where Na is equal to 6.022 into 10 to the power 23 per mole. Hence, A is equal to 1 divided by 6.022 into 10 to the power 23 into 1.998 into 10 to the power minus 6. That is equal to 8.30 into 10 to the power minus 19 meter square. Now we'll see the step 2, convert to Armstrong square. Since 1 Armstrong square is equal to 10 to the power minus 20 meter square, so A is equal to 8.30 into 10 to the power minus 19 divided by 10 to the power minus 20. That is equal to 83 Armstrong square. So here the final answer will be 83 Armstrong square, that corresponds to option C. So here option C is the correct answer. I hope you understood this video. If you like this video, please like, share and subscribe to my channel. In next video I will solve GATE previous year questions. Thank you. Have a good day.